Hello, young chemists. What's up? My name is Mr. Rosen. Here to go over some practice problems related to gas stoichiometry. Many of these are like the mass-to-mass stoichiometry problems we learned earlier in the year, but the gas side of things allows us to go to and from volumes of gas. So we're going to work some of these practice problems. A couple of ideas or concepts before we get going here. In the 1800s, Avogadro, who we've talked about in the past, that's the big name associated with the idea of a mole. Avogadro proposed the idea that equal volumes of gas at the same temperature and pressure contain the same number of particles. This came to be known as Avogadro's law. Now, notice that the temperature and pressure were specified. If scientists are working with data sets and they're looking at gases, it's easy to have a standard set of conditions so that kind of everyone's on the same page in terms of the temperature and the pressure. If either of those is different, then the other values will change. So STP stands for standard temperature and pressure. That is, standard temperature is 0 degrees Celsius and the pressure is 1 atmosphere of pressure. This is essentially the temperature that water freezes at sea level. 1 mole of gas at STP has a volume of 22.4 liters. Okay, and you can find this if you were to plug in the values of STP to the ideal gas law, you would get the molar volume of a gas. Okay, and actually, just on second thought, I could do that real quick, just to help you out in terms of where does that number come from. 1 mole of gas at STP is equal to 22.4 liters. Okay, where does that come from? Well, if you use PV equals nRT, right, where the pressure is 1 atmosphere, that's standard pressure, and the temperature is 0 degrees Celsius, which is 273 Kelvin, that equals 1 mole of gas. This is supposed to be our volume. I apologize for that. 0.08206, that's liter atmospheres over Kelvin mole. And then our temperature is 273 Kelvin. Sorry about that. If we plug standard temperature and pressure into the ideal gas law, where this is your pressure, 1 atmosphere, and this is your temperature, okay, and we solve for volume, right? To solve for volume, you divide by 1 atmosphere on both sides, and that leaves you with V. Okay, whatever we do to one side, we do to the other. We divide by 1 atmosphere. All units will cancel out, and we will be left with only 1 unit, which is volume in liters. Okay, so that's 1 times 0.08206 times 273 divided by 1, and you can see what we get here, 22.4 liters. All right, so the volume of 1 mole of gas at standard temperature and pressure, 1 atmosphere and 0 degrees Celsius, right, gives you 22.4 liters. So you can plug it into the ideal gas law to find that, but that's called the molar volume of a gas. Okay, the molar volume of a gas. So simple calculations here, gas stoichiometry rating calculation says, what volume does 39 grams of chlorine gas occupy at STP? So we know that at STP, 1 mole is 22.4 liters. Sorry, that's off the page a little bit. Okay, 1 mole is 22.4 liters. We just need to figure out how many moles this is, and then we can use that. So we're going to convert 39 grams of chlorine gas, which is Cl2, to moles. 1 mole of Cl2 gas is some number of grams. And if we look on the periodic table, chlorine has a molar mass of 35.45 grams per mole, and there are 2 of them, which is 70.9 grams per mole. If we do this, grams will cancel, and we'll be left with our moles of chlorine. So 39 divided by 79.9. I'm just going to do a little rounding here, but I'll leave it in my calculator, but just to jot this down, 0.488, this is now moles of chlorine. Okay, now, as I mentioned, 1 mole of gas at STP is 22.4 liters. We have a little bit less than a half a mole. So, a half a mole would be, 11.2 liters. This is a little bit less than that, so maybe like somewhere between 10 and 11 liters is what we'd expect. But let's not guess, let's actually do the math. So we're going to convert from moles to liters using the molar volume of a gas. This is moles of chlorine, and we want to turn to liters, so liters goes on top. 1 mole of gas, doesn't matter that it's chlorine, but 1 mole of gas at STP is 22.4 liters. So we're simply taking, and I'm just leaving this in the calculator from before, times 22.4. What I get is a number very close to 11, 10.9, and that's liters of chlorine. So this is just a simple problem where you're given the grams of something and you have to find the volume. You just use the molar volume of a gas. 1 mole is 22.4 liters, so we just figure out how many moles we have, and then we turn it into liters. A more typical gas stoichiometry problem is more similar to a mass-to-mass stoichiometry problem. So a mass-to-mass stoichiometry problem, you are given grams of something and you're going to grams of something else. But in this case, you are given grams of something and you're solving for volume of something else. So in this case, that means your answer is going to come out in liters. So instead of going from grams to grams, we're going from grams to liters. And it's actually even easier than mass to mass because the last step is the same for all of them. So step 1, convert from grams of methane to moles of methane. So we're going to take 223 grams of C3H8, and we're going to turn that into moles. Okay, 1 mole of C3H8 is some number of grams. Okay, now carbon is 12.01, and there are 3 of them. Hydrogen is 1.01, and there are 8 of them. So we add those together, and we get 44.11. That is the molar mass of our propane. That's a 3. So if we take 223 and we divide it by that number, we get about 5, sorry for the glare, you get about 5 moles. I'm going to leave this in my calculator, okay, but just for you to see, I'm going to jot down 5.055 mole of C3H8. Okay. Now, we need to go from moles of C3H8 to moles of what we're trying to find, which is CO2. So we're going to use the mole ratio from the balanced equation to convert from moles of C3H8 to moles of what we're trying to find. So moles of CO2 goes on top, and moles of what we have, C3H8, goes on bottom. Now these numbers are going to be based on the balanced equation. We're going from moles of C3H8 to moles of CO2. In front of CO2 we have a 3, so I'm going to put a 3 here. And in front of C3H8 there is nothing, which is the same as a 1. So I'm taking my number of moles and multiplying it by 3. Moles of C3H8 will cancel out, and this will give me my answer, which will be in moles of CO2. Now I still have this number in my calculator, so I'm just going to take this number and multiply it by 3, okay? 15.7 or 15.17-ish, 15.17-ish. Now I'm just jotting this down so that you can see it, but I'm leaving it in my calculator the whole time, okay? So we converted from grams to moles by dividing by the molar mass, and then we took moles of what's given and converted it to moles of what we're trying to find using the balanced equation. Now, the question doesn't ask you how many moles of CO2 gas will be produced. It asks us what volume of CO2 gas will be produced. And we know how many moles it is, right? And we also know that 1 mole is 22.4 liters. So if 1 mole is 22.4 liters, 2 moles would be 44.8 liters, right? 3 moles would be 3 times this number, right? 67.2 liters, and so on. We're going to take our number of moles times the molar volume of a gas to convert to liters, right? So the final step is to convert from moles to liters. And to do that, we will take our number of moles, which is about 15.17. This is moles of CO2. And we're converting it to liters. So liters goes on top, and what we have, moles, goes on bottom. 1 mole of CO2 at STP is 22.4 liters. So we're taking our number of moles, this is still in my calculator here, times 22.4. And what we get is our volume in liters, okay? I'll round this to 3 significant figures, which would be 340 with a decimal point liters of CO2 produced. This is a typical gas stoichiometry problem. It's just like a mass-to-mass stoichiometry problem, but the last step, instead of converting from moles back to grams, you go from moles to liters, and you do that using the molar volume of a gas. So we'll do a couple of practice problems. These ones I'll do a little bit more quickly now that we took time on that. So it says zinc metal reacts with chlorine gas to form zinc chloride according to the following equation. What volume of chlorine gas at STP is required to react completely with 35.1 grams of zinc? Okay, so we're going to write what's given, and I'm going to do this in a list. I'm not going to break it down so much. Well, actually, maybe I will. We'll just break it down. You can do this just stringing it all together in one calculation. 35.1 grams of zinc. Okay, so first we're going to turn that into moles of zinc. 1 mole of zinc is some number of grams. Okay, so zinc has a molar mass of 65.39 grams. Now I'm going to leave this in my calculator, but I'll jot down the brief answer on the page. 35.1 divided by 65.39. We get a number. It's about a half a mole, a little bit more than a half a mole, 0.537 moles of zinc. Okay. We're then going to go from moles of zinc to moles of what we're trying to find. So moles of zinc is on bottom because we want to cancel that. And what we're trying to find in this case is chlorine gas. So moles of chlorine goes on top. Now this is just a mole to mole conversion. We are given moles and we're going to moles of something else. This will give us our answer here in moles of Cl2. According to the balanced equation, this is balanced and there are no coefficients, so it's just a 1 in front of all these. So this is a 1 over 1. Okay, so that means even though moles of zinc in terms of units cancels out, we get the same number, 0.537-ish moles of chlorine. Now again, it's not asking us for moles, it's asking us for volume. So volume means liters. So we're going to take that number, the number of moles of chlorine gas, and turn it into liters. 1 mole of chlorine at STP has a volume of 22.4 liters. So with this number still in my calculator, I say times 22.4, and I get about 12, and that's liters, right? So moles of chlorine cancels out, and I'm left with 12.0 liters of chlorine gas. So we went from grams of what's given to moles of what's given by dividing by its molar mass. We then went from moles of what's given to moles of what we're trying to find using the mole ratio from the balanced equation. And then we went from moles of what we're trying to find to volume of what we're trying to find, liters, using the molar volume of a gas. Notice every time we use this same number here. Okay, so it doesn't matter if it's chlorine gas or it's bromine gas or carbon dioxide. 1 mole of it is 22.4 liters. All right. The final problem here is actually written a little bit differently. It says, what mass of pH3 will be produced by the complete reaction of 8.5 liters of hydrogen gas? So in this case, we're actually given liters, and we have to work to mass of product. So we start by writing what's given, 8.5 liters of H2, and we're going to turn that into moles. So to do that, 1 mole of H2 is some number of, and what we have liters here, we need to cancel, so liters goes on bottom. 1 mole at STP is how many liters? 22.4 liters. So see, in this case, we're going the other direction. Instead of going from moles to liters by multiplying by 22.4, we're going from liters to moles by dividing by 22.4. So on the calculator here, that's 8.5 divided by 22.4 gives us a little more than 1/3 of a mole. Again, I'll just jot this down, but I'm going to leave it in my calculator. That's 0.379. This is now moles of H2. Now that we have moles of H2, we're going to convert from moles of H2 to moles of what we're trying to find, which is pH3. So that means pH3 goes on top and H2 goes on bottom. And we're just going to use the mole ratios from the balanced equation. So in the balanced equation, there is a 4 in front of pH3. So I'm going to put a 4 here. And there's a 6 in front of hydrogen. So I'm going to put a 6 here. So we are going to take this number, which again, I'm leaving in the calculator here, is going to be multiplied by 4 divided by 6. And this number now, 0.253, is moles of hydrogen cancels. This is now moles of pH3. The question's not asking you for what moles of pH3 will produce. It's asking you what mass of pH3, and mass means grams. So we're going to take our moles of pH3, which is about 0.253 moles pH3, and we're going to turn it into grams. So 1 mole of pH3 is some number of grams. So we have to add up the molar mass for that. Okay, so phosphorus, I'm actually just going to do this in one step on my calculator. So phosphorus is 30.97 grams per mole. So 30.97, I'll just jot this over here, 30.97, and then 3 hydrogens. Hydrogen's 1.01, so that's 3.03. Okay, so if we add that up, you get 34 exactly. So this is 34 grams per mole. So we're going to take our number of moles times 34. We get 8.60. This is now, moles cancels, this is now grams of pH3. That's how much pH3 will be produced by the reaction of 8.5 liters of hydrogen. So this has been a video going through some gas stoichiometry problems. Like I said, it's just like the mass-to-mass stoichiometry problems, but the big concept is that 1 mole of gas at STP occupies a volume of 22.4 liters. And again, STP is standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure. Hope this has been helpful. Gas stoichiometry, good job. Keep up the hard work.